hope I can start now. People in Zoom, can you hear me? Can you hear me on Zoom?
Yes.
Okay, good. So I guess I should share the screen. And now I'm going to turn on my slide. Yes. Okay. So today we are going to finish off the consumer and start with some producer. So let me also download this. No. So let us very briefly review what the consumer problem we're working on. So so why we are working on consumer is because of we try to model human rational behavior, as most of you are working on B school or computer science, right? So basically modeling how human makes decision will be important. I mean, the next topic which we should cover the second half today is we're talking about firm, and for firm usually is much easier to describe because and we know this most of the time we have a firm that is mainly for profit making, or an NGO is focusing on some objective they have in their mind, that we have a clear objective. And also even now we call the even style still talk about the ESG, right? Environmental, social responsibility, those kind of stuff, or governance, and they still a kind of mix of profit maximizing and some social responsibilities, and it's easy to describe. But human, by and large, is a little bit more difficult than because more idiosyncratic, taste, bias, all the things is making things more difficult. But then how can we start? Then we start from assuming most basic thing is preference, and we don't go beyond preference. That would be psychology or neuron science idea. We just assume the preference. We start with the human have capability to compare bundles, and we assume people call rational if they satisfy two criteria. Is what we call completeness. Given you two different bundles, you would be able to tell which one is better than the other, right? And you can't say you can't compare, okay? And we have some minimum assumption on consistency, which we call transitivity, which said if x you say is no less than y and y no less than z, then x should be no less than z, okay? And there's no cycle in the other word, right? Because if z is bigger than x, then you don't know which to choose, right? So that is the idea. Is like you can tell which one is better, and if I give you two options each time, right? I will not end up in cycle, okay? So that is the thing, right? Completeness make sure that we can compare. Transitivity makes sure that we don't end up in cycle. So that's why you can always reduce the problem into comparing two things, right? Because of the transitivity makes the case much easier. Otherwise, if you don't have this, we have to consider all the cases, right? Suppose I have give you 3 bundles, what are you going to choose? 4 bundles, you're going to choose. Then the model is not going to we will need a lot of assumption. So this is very strong, okay? The transitivity. So as I said, rational preference is complete and transitive, and we can, from the preference, we can define indifference, okay? We can also define strict preference, okay? Indifference means they both know better than the other, right? No worse than the other. Then strict preference is strictly better, right? It's one of them is so, but not the other way around, okay? And from that, we define some property about preference, okay? And remember, the reason why I want to do that is because these assumptions will translate themselves into utility, right? And as most often the case we work on utility, right? We make assumption on utility, then we need to know what do you mean by that, right? On the primitive, the preference. So that's why we study some property on preference, and we will know how it means in the utility. Okay. So here we have local satiation, right? Just like there's always something good nearby, right? And in some sense, if you talk about utility, there's no local maximum in the utility function, right? If there's local maximum, then you violate this idea, right? And we have monotonic, right? Which means that the commodity we're talking about are goods, right? More cannot be worse off, right? And strictly more is actually strictly better off. Okay, so these are two versions, and more often than not, we rely on the strongest version in most of the cases, right? So it's not a big deal. Just like it just means the north-east direction is always better, right? When you move in difference curve, I mean, level up, you go to the northeast direction. Okay. And the next is continuity. This continuous preference just mean that the simplest thing is mean that if use this one is better, use X is preferred to Y, and you can always find something nearby X to Y for this strict preference continue to hold. So it means if A is X better than strict better than Y, and there's something nearby, this continue to true. So you will not suddenly reverse your preference. So this is technical, but indeed this technical is very appealing. But you can imagine that some scenario this is not true. Say for example, as I mentioned in the last class, a lot of time when humans make decisions, it's more like lexicographic preference, right? You decide things one by one, right? When I mentioned to you last class, in the people's part, the marriage market, in that case, when men and women seeking friendship, romantic friendship or marriage partner, they would have limit on age first, I guess, right? And then on whether they have house, their kuko, their salary, so on and so forth, right? One by one, right? Cannot, I mean, people have different criteria, but they will say this criteria have to be fixed first before they go to the next one. And sometimes you may ask how rational is this, right? It's not fully rational, but sometimes when the set of choice is too large, then you would do this, right? Because this a kind of screening, right? You screen one by one, and it's difficult to decide things. So that's why you do screening. Okay, you choose this first, and then goes on. And the next is convexity. Convexity is related to mixing bundle, right? It's just like if X prefer to Y, mixing them is better than the weaker bundle. Okay. You may ask why we care about this convexity. This is indeed is driven by the fact that we would like to assume our utility is quasi-concave to ensure the maximum would exist in a utility maximization problem. So it's rather than driven by our desire for the preference, actually we define technically from our utility, right? Because you can imagine if you have convex preference, then you can easily solve the problem. If you don't have convexity, then things become much more complicated. You're likely to have some corner solution and so on and so forth. So it's more like technical, but it do have some intuitive appealing property, because mixing things should not be worse off. Okay, you can imagine this kind of somewhat continuity favor, right? Just like X is better than this would continue to hold. Okay, but anyway, let me continue with utility, right? Utility is just simply the way you represent the preference. Okay, and higher the number, the better. So the idea is just like the bundle is an n-dimensional vector, right? You have preference over it, but now this is a complicated object to work with preference. Maximizing over binary relation is doable in math, but we cannot use calculus, right? Then you have to use the optimization technique to handle the problem, right? It is not easy to do. So that's why we're trying to see if we can boil down you can see the consumption space to real number. In that case, we just map everything into real number, right? And back to real number, we know how to do it because it's simply calculus problem. So basically, just like we don't know how to handle this, then we just make mapping, right? Make a connection between the commodity space to the real number, right? A number line, then we know how to do. Okay, it's easy to do when you have real number, right? And because this mapping is not one-to-one, right? Because it's like as long as this thing would hold, right? So this actually means that this utility is a ordinal sense, right? You can make any monotonic transformation, then this utility will still works out nice. And last class, we spent some time on proving this existence of utility, right? What we said is continuous strict preference, monotone preference will imply the existence of utility function, right? So I add this to the slide because I think they will be useful, right? But just go back to the proof quickly. So for any bundle X, right? B under strict monotone preference, B is worse than X, right? A is better than X, right? And by continuity and also by the difference of preference, there must be something in the middle that's indifferent, right? Because you keep going, then you cannot suddenly flip, right? This is the idea of continuity. There must exist somewhere in the middle, the alpha E, right? And that's called alpha is actually we call the number utility, right? And this first graph shows you every bundle, you can find number on this 45-degree diagonal, right? And the next thing is to show this number actually is a utility in the sense that the higher the number, right, mean the preference is more, the bundle is more preferable, right? So look at this is by construction, we have a bundle X and bundle Y. X is better than Y, okay? And it's not clear the case because monotonicity just means that anything in the northeast about X is better, right? It doesn't say anything about both in the right and below, right? You don't know, but let's by construction X better than Y, okay? And by what we have done in the diagram here, for any bundle X, you can find a bundle on the diagonal, okay? And that is same, right? And same for Y, okay? Now we claim X is better than Y, right? But by construction, U of E is indifferent to X, right? U of Y, E is indifferent to Y, right? So this bundle must be better than this bundle, right? By construction, because that is coming from transitivity, okay? Although we didn't prove it, but actually we can prove it. Transitivity imply if X is indifferent to Y and Y is different to Z, then X also indifferent to Z, right? This thing can actually, I mean, you can, transitivity means that, I mean, the indifference, actually you can treat it as equal, right? And everything, actually the way you do inequality would continue to hold, okay? And you say that this bundle is better than this bundle, right? But because of monotonicity, right? This means that this number is bigger than this number, okay? So you prove that when X is better than Y, then the way you define utility, you give it this, okay? So that is the construction based on continuous and strict monotone preference. Of course, there are many proofs that actually don't rely on monotonicity, but we just use it because the book also use it, so we just don't get into more details on things. And here, additional benefit of this construction is there exists a continuous utility function. Okay, that means for the utility we construct non-exists, and we can able to use a continuous utility function to represent it. Okay, so that solve the problem, right? Because we always assume continuous utility, right? Because otherwise, I mean, there's no point of using calculus, right? And of course, at the one more end, you want to see when do you have differentiable utility, right? But it is beyond the scope we're doing. I mean, of course, you can check out the textbook to see what is what is a differentiable preference. Okay, but we don't go into that detail because of the fact that we have continuous utility function. Usually, unless a special case, we can always find a monotonic transformation of the utility function so that it's a differentiable. Okay, in most of the case, but I mean, there's some case not, but at least in the limiting case, you cannot. You can do it. Okay, later you will see, right? Like the max, the less, one is not right. Leontief preference is not right, but later you see when I take the CES utility to the infinity, it is included in the case. So it's not, even though it's not fully differentiable, in the limiting case, I can use a continuous differentiable function to approximate that. So it's not a big problem. Okay. And next is I just remind you we have some assumption on the utility, right? The most important what we're trying to do is the quasi-concave utility, right? Just saying that if you try to mix the two bundle, this is better than minimum of the original bundle. Okay, mixing is always better off. And just to important thing is quasi-concave imply convex, right? So strict quasi-concave implies strictly convex. And why we care about this, right? All this thing, right? I mean, this is the monotonic preference mean monotonic utility, increasing utility. Strictly convex preference means quasi-concave utility. So why we care about this is because later when we talk about utility function, right? The maximization problem, if strictly quasi-concave, is always unique. So that is the main thing. Okay. So let's go back, continue our discussion. So why this marginal substitution, right? It's important but you learn it in your undergrad anyway. But it just what it means is just like if I give one unit of I in this case, I define, and then how many unit of J I will get in order to make my utility the same. Okay, so it's just like it just considered as an internal exchange rate, right? To you, if you give me one unit of I, okay, and how many J I want to sacrifice, right? Or I give up I, how many J I need to make me as happy as before. Okay, so that if you look at this, it's basically if you draw it in the diagram in the two good world, it's just the slope of indifference curve. Okay, because you make utility the same. Okay, so there's remember there's three special cases: perfect substitutes, perfect complement, and coplocalus. All these three are important in the sense that when you try to develop your work, I recommend you start with this example first, because if this example works well, then likely your problem would work well, right? Of course, you can see a lot of papers start with something very complicated. For some time, it is good to start with complicated preference only if they simplify the math. Okay, if not, I recommend you start with something a little bit more specific. Okay, this is one way. Usually, some tips you try to develop your own model is try not to start with something very complicated you can't handle. Start with something very stupid thing and then add up. It's easier than start from general. But if you're good at math, then you can start with general thing. Not a big deal. Okay. So let's consider the utility maximization problem. Okay. here we take the price as given, okay? So that is what distinguishes the consumer theory with the IO or the game field literature, where everyone making decision is taking the environment a constant, okay? It's not what they're going to do. It's not going to change the environment, okay? Take environment as given, okay? In this case, the interest of the market, that is the market is a price take. So that's why they take the price as given, okay? The interest of the market consists of many people, okay? In that case, he is small compared to the market, so there's no way he can change the market. So that's why it's good assumption, okay? But in the real world, a lot of the cases, you interact with only a few people, okay? Then these kind of assumption can be problematic, right? And in many scenarios, your interaction is with other people. It just can be a very limited number of them, right? Say in this room, right? You interact with me, right? A classmate, right? Just feel of, right? It's what you're doing is affecting the environment, right? Supposed to making very loud noise, or you take your phone and talk, right? Then you affect everyone, right? But you consider the world, right? You pick up my phone and talk, you shouldn't affect people in the other class, right? So there's an idea to think carefully what we are doing right now, okay? This assumption is good when the market is big enough, you're interacting, right? So that's why if you look at the finance literature, right, look at the trading literature, right, when you talk about individual investor, you would take this assumption is fine, right? But if you are institutional investor, you're a fund manager, this is not very good, right? Because how much you're buying or is not going to is going to different, right? So you look at, say, market microstructure literature, right? You will see uninformed trader, which a lot of them, right? They don't know the inside information. In that case, it's okay to assume price taker. But if they are informed trader, right? And what they're doing actually review the information, those kind of things, right? Or they move the market. So that's things are different, right? Just like Elon Musk, right? Try to sell his stock, the market move accordingly, right? So that's the idea, okay? So the next thing is try to represent this the budget constraint. Again, we are here, we can see the income is also exogenous, right? So in later you will see, I mean, if you apply this to the model of labor economics, right? This income is not something unmoved, right? Because the more you work, the more money you gain, right? In that case, your budget is not a fixed thing, okay? But in our model, it's okay because they are just price takers. Even we consider they, just like the money comes from somewhere down, okay? So that is a simplifying assumption, right? When you talk about general equilibrium, you talk about labor market, and this kind of thing is a little bit trickier, okay? But anyway, in our model, like here, we just make our life easier. We assume that money coming from the heaven or money coming from pick up from the street, you can have some money and consume, okay? And most of the cases fine because the money you earn from the employer usually is unaffected by how much you spend your money, right? You will not affect, I go to buy a KFC, McDonald's, where you affect the money in my bank account now or in the future, right? You're too small to affect anything. So it's not a big deal, okay? Here, just go back to this very important question of utility maximization, right? So you just maximize, you're choosing a bundle. Why the maximization problem is that simple is because two things I mentioned. You take the price as given, income is given, okay, in this framework, okay? If not, then the model is more complicated, okay? Just let you know, to remind you that although it looks very simple, you have to notice what assumption we make to make this simple, okay? We make the price exogenous, we make the income exogenous as well, okay? And we don't have any other constraint, right? There's no physical constraint in this world, okay? You can buy as many as you want, right? And suppose this is there's a one good is called iPhone, right? And you know at the moment, right, iPhone is ration, right? Even though you have billions of dollars, you cannot buy more than 10 iPhone, I guess, right? So unless you go to second-hand market, but there's something is ration. You cannot buy things, right? Say suppose X is like the health, right? And we know there's some good that's not in the market, right? Even though as long as you want to do more health or you have more leisure, there's some limitation, but we do not include it in our model. Okay. Now, just to here, just some math problem, not math problem, but require some math statement. I don't think we need to go about it because I guess most of us is not using this result, because when we work on applied problem, a maximum is always guaranteed. Okay, you're doing the thing, you can find the solution is not usually easy. But how to guarantee this problem has a solution is a continuous U, and B is a compact, actually bounded and closed. Okay, a compact set with a continuous objective function, you always have a solution. Is what we call from a math theorem. Okay, and some of you try to study the first time study the microeconomic theory, you notice that we are actually a lot of results actually borrow from math. So you may be tempted to think you need a lot of math. It's true if you go to the econ department, okay, but we are in the apply, so you don't need to worry too much about that. Okay, so as long as you understand, basically you need to remember, right? And then this is fine. And I don't think you need to remember even for this result, but I just put it there. So as long as you're okay with your assignment, okay, and then you shouldn't have any problem. Okay, and to be honest, I mean, for me, even I do kind of apply theories. I'm doing theory, then I don't recall every result there. Okay, if I'm teaching, of course I remember, but if I'm teaching, I'm not going to remember every single thing. I mean, of course I can pick up easily, but since I have learned it, right? But usually you don't need to worry about the math as long as you understand what's going on there. Okay, you just when you do theory, I mean, you need the math, you just pick up when you need. Okay, at least for me, I mean, of course, people are math genius, have no problem learning difficult math and do it. But I'm just a normal person. Okay, it's not a genius style. I mean, if you ask the genius people, then they will tell you that study more math and then would be helpful, but not the way I do. So here the next thing is quasi-concave is important assumption we have mentioned all the time, because it makes sure that the maximum is unique, right? The reason is very simple. Just want to emphasize the math here is because if there are two solutions, right, means that they have higher utility for you, right? But quasi-concave means combining the two. Okay, the linear combination should be strictly better, but this linear combination is feasible, right? Just like this, right? Because suppose a bundle A and bundle B, they are maximum, right? So that means that UA equal to UB, right, is bigger than, less than, or anything in the budget set, right? They're the best. Okay, but you know the linear combination of, say, lambda A plus 1 minus lambda B, okay, is even better than this two, right? And this is feasible. Okay, because if you can, your money is sufficient to cover A and cover B, right? So it will cover this, right? Because the price doesn't change based on how you consume, right? The linear combination is still within the budget set, right? Because your budget set is like this, right? It's a convex. So anything here is for A and B, right? Anything in the middle also feasible, right? So because it comes from the convex of the budget set. Okay, so this is also feasible. So this is better. So it violates the idea that you have two number, your two bundle that is good. But anyway, this is just to try to show you that some math there, but anyway. But anyway, when you apply, you always quasi-concave. So I don't see then you just make sure that you are not worried about the existence or uniqueness. Okay, because in general, when you derive a model, you have to worry about whether the solution exists, and also they will be unique if you try to build up your own model. Okay, especially when we talk about game theory. Okay, When game theory, when you do it, you have to super careful about whether the equilibrium exists. Okay, and if none exists, it's not difficult, but you try to see if there are other equilibrium exists, especially the corner solution will be important in game theory. And also you have a many dimension of stuff. Okay, say in complementary, you have belief, you have those kind of things, then you have to worry a lot of stuff. But in that case, it's very nice. You have caustic concave and unique. Okay, and here we have Wawa's law. The Wawa's law is rather simple. Actually, you don't need math. I mean, you can just use your intuition, can see, right? Because when U is monotonic, okay, means that more the better, right? The budget constraint must be binding because they're good, right? So it means that you would use up all the money. So there's nothing new there, but I'm not going to do the proof, the math, but it's simple. And here is the first result. We're assuming differentiable, we're assuming caustic concave, okay? In that case, we have a unique optimum bundle, right? And assuming we have interior solution, okay? Okay. Do note that we said here maximum is unique doesn't imply anything about interior or corner solution. Okay, it doesn't say anything about corner solution or interior solution. Okay, so assume it's interior solution. What we get is the margin rate substitution should be equal to price ratio. Okay, the intuition is very simple, as we said last class. It's like the MRS is the internal exchange rate, right? How much you willing to change one good to the other, making your utility the same. Okay, and this is the budget line, right? It's the slope of the budget line, and this is the external exchange rate, right? You can exchange X and Y, keeping your budget constant, right? So so and you can always swap X and Y in the external market. Okay, there's no implication, except no budget implication, right? Here means you can always swap your bundle without any utility implication, right? It must be the case they're the same, right? Because if not, you can always go out and change, right? Is exactly the idea behind the Hong Kong exchange rate peg, right? The Hong Kong Monetary Authority always say, you get $1 US from me, I give you 780 Hong Kong dollar, right? So if you're happy with that, you can always swap anyway. Okay, the two-way exchange, right? The same here. You can always swap I to J, whatever you want, right? So it must be the case that the outside exchange rate same as the inside, right? Otherwise, you have either consume more I or consume more J. Okay, but in the other word, it just means the following, right? It just means that the budget set here, your indifference curve, assuming caustic concave one, will be a convex like this, right? This means that the optimum bundle must be at the point where the tangent is same as the budget line. Okay, this is what it means. I mean, you learn it in your undergraduate or an introduction to micro, so it's not something new here. Okay, and how do you derive that result? I think this is important because this is the minimum math we need for our class. Okay, if you okay with that, then it should not be an issue. If you are struggling with Lagrangian, then I recommend either you do some math, okay, or you don't take this class, okay, or you should go back to your intermediate. You should also take the intermediate micro, okay, because this is already in the intermediate micro, say in the econ department, okay. Conductor will be more than what we need, okay. But I think at least you should know Lagrangian, okay. For Lagrangian, you have, I'm not going to explain Lagrangian, okay. So suppose Lagrangian, and under the idea of we have caustic concave, I mean, there's a math idea is if you have caustic concave reference under and a linear constraint under Lagrangian, the FOC is also sufficient. Okay, probably you already know it anyway. So this is the first order condition, right? That's the first derivative, and turn out the solution to this is also sufficient condition. Okay, so we don't need to check XOC. Okay, but anyway, no matter what, but even this is necessary. But given we know is caustic is a we know the maximum is unit, right? So that's already sufficient already. Okay. So this is you solve it out, then it basically give you the idea of this, right? This is the Wawa's law, right? Actually coming from the monotonic preference as well, right? And this is marginal utility for one good is equal to the price times lambda. Okay, so that's why people interpret lambda, what we call marginal utility wealth. Okay, and actually coming from what we call the envelope theorem, right? You differentiate the utility with respect to the income at the optimal is lambda. Okay, so what it means is if I give you one more, we give the guy one more unit of income, what is the increase in his optimal utility? Okay, will be lambda. Okay, lambda with number you solve, right? Remember in this model, you will solve for all the x and lambda. Okay, lambda is also a variable in this model. Okay, and so that means that this FOC means your marginal utility on x. Okay, suppose I ask to give you one more unit of I. Okay, this is how much gain you have. Okay, and the left hand side is if you want to buy one more unit of I, you need PI, right? You need cost of PI. Okay, this money to you worth lambda utility. Okay, okay. So in the optimal, they're the same. Okay, because the right hand side, so the left hand side is how much you gain by giving you one more unit. Okay, and the right hand side is how much how the utility, the cost of the giving one more unit, right? Because if you get one more unit, right? You get one more unit, you have to pay this much, and this much will worth to you lambda. Okay, so that is the idea of this statement. Okay, from this statement, although we don't do conductor, okay, actually should do conductor, but I mean because our class don't do conductor, that means that when a corner solution, you should expect this happen, right? Because how much utility you gain is less than how much it costs to you, right? So that is the idea. But we are not doing conductor. But if you do conductor, then you know this is something standard. And in case you want to know detailed discussion on conductor, you can look at a textbook, right? The Randy textbook will be a good way to look at. I mean, if you want to look at it first time, but I guess we don't do conductor for our class, so it's not a big deal. Okay, and here just add a new slide, just saying this statement here. Okay, and why this is true, right? You can prove it. You look at the Randy's textbook, but the idea what we have is because FOC is a necessary condition, right? And we have this is unique, right? So you don't have a problem to that. Okay, so this is a unit. So if basically if this is whole, which is also always the case for our application, so you don't have a problem. Okay, just solve this Lagrangian, then you're done. Okay, so it looks very simple. Okay, but do remind you that because of the many simplification here we've done, right, to make it work, right? Because to make it this project is a linear, we also make this as quasi-concave, so everything is simpler. If not the case, then things can be more problematic. Okay, but for the classical consumer fee, we don't have this problem. Okay, so after this, we have a Marshallian demand, right? Marshallian demand will be you solve this optimal solution which says you need, and this point will be the demand function. Okay, and once of this demand function, we stop at this line. The last time, okay, we have the first property will be if you multiply everything by fixed constant, then the value becomes the same, right? There's no, if you double the prices and double the income, should not change anything. Okay, Usually that's called no money illusion, or that is like rescaling the money metrics to not affect, right? Or in the case where inflation, okay, but a particular inflation where income and price move up, right? Then it's not change. And you may ask, right, why people are worried about inflation, right? If people follow this model, right? The problem is for inflation now is the price goes up, but the income does not. Okay, so the inflation, what you meant in the real world is not exactly this inflation. Okay, it's the wage is sticky in terms of macro idea, but the price move up, but the wages does not. So people complain. Okay, if my wage goes up with the inflation, okay, actually I don't have anything to complain. Okay, but the real world is not the case. Okay, and you can see from this what we call in mathematics called homogeneous degree zero. Okay, and in terms of map, just like this, right? Just like this, x of lambda x is f of x. So this is the and when we have this, according to mathematician Euler, okay, there are a lot of property you can derive. Okay, so that's why in the textbook you can see some of you actually asked me, okay, Mascola, Winston, Green textbook, they spend a lot of time working on this. Okay, because of this this is a homogeneous degree zero equation, you can derive a lot of math property, and that would be useful in the old days. Okay, and now I don't think any people work on that. Maybe some people, I don't say no, but it's not. Well, if you pick up a journal in economics, you actually don't see anything about discussion on elasticity of those kind of that. So that's why I take it out from my slides. We'll not talk about that. But if you want, you can go ahead to work on those. Okay. So we save time. We are working on the following: how demand change with income, on price, and other price. Okay. So the Marshallian demand is the most complicated. Later you will see compared to others that we can't say anything beside homogeneous degree zero. Okay. And we cannot say when price goes up, what happened? When income goes up, what happened? We don't know. So that's why the Marshallian demand is the most complicated object to work with. Later you can see we have a Hicksian demand or compensating demand or other function or indirect utility function. Things are more clear. For Marshallian demand, it's very complicated. Okay, and basically we don't have any theoretical prediction. Okay, we can do some further breakdown. Okay, but we cannot say more than that. Okay, so here I want to go with you with this example because something, and then we'll break because something similar will appear in your assignment. Okay, so let's look at this problem. Okay, utility function. Okay, and you can easily see that this is continuous, this is monotone, and you can try to draw it. It's also a convex or causic, or what we call quasi-concave utility, right? You try to draw it. All right. If you try to draw this is actually this, right? The utility function like this. All right. So it's a convex. Okay. Of course, you can prove it, but by simply looking, it's already fine. Okay. And so Lagrangian, as we said, continuous bound set maximum exists and is unique, right? So the FOC is sufficient. Okay. Then you do FOC, right? Just you differentiate that. I don't think I need to go line by line. Is that okay? So this is you differentiate this, you get with this, right? You differentiate this, you get with this one. Okay. And from this on, what we're going to do is to you just divide the first two equations, give you the MRS like this, right? Because you divide these two is x1, x2 for x1, and then this p1 over p2. Okay, so that is the MRS. Okay, and that implies one interesting thing. is the total expenditure on good one is same as x2 for good two. Okay. So because you consume the whole budget, means that half of money go to good one, half money go to good two, regardless of how much they are. Okay, so that is an interesting result, right? So that's what we have is, and how much you consume, right? Because half the budget go to good one, right? So just y over 2 of p1, right? X2 is y over 2 p2. Okay, so that is the result, and it's orthogonal, and with special case is the exponent is 1/2. Okay, and probably I asked you a little bit more complicated than this, or somewhat related question in your assignment. Okay, so I think let's a break, and then we will continue. Okay. Let me quickly finish the rest because the rest will be more like listing of result rather than we are not going to derive them. So we just go over them quickly because shouldn't be an issue. Okay. So as we said at the beginning, okay, before the break, we said the Marshallian demand function actually is too flexible to do many things, right? It's good for empirics, but it's not good for theory because you can't tell anything, right? Just like if income goes up, are you going to consume more on certain good? It's not there, okay? So that's why when you see this, right, a normal good means if your income goes up, is it going to consume more, right? In this case, look at this problem. Income goes up, you consume more, right? But in the case also like this graph, right? For good X is inferior, right? Because if you goes up, right? Income goes up, right? Actually consume less of one, okay? So it's not immediately clear whether income goes up is good news for your firm, right? Right? Because if your firm is selling the product which is inferior good, right? Then it's not the case that you're getting better off, right? So here introduce something. It has been discussed very long time in the literature in the old days, but now no, I don't think any people discuss anymore. But it is still in the footnote in the textbook. It's called ordinary good and the given good. We said if the price of its own price goes down, okay, do we expect you consume more, right? Let's go back in the last class. We said what we want is we want as a preference, we want to have what we call we want this happen, right? Because at the end of the day, right, we want from the beginning, we want P of X, right? We want this happen. We want the demand function, or we call inverse demand function. We want it to be downward sloping, right? This is something what we want to have at the end of the day. But turn out, as I said, or as we see here, it's not clear. Theory is still possible that the price goes down in this case, right? Your demand can go down. Okay, there's no easy way to say this cannot happen. Okay, and later you see when you have Slutsky equation, this would happen if this is inferior good and the income effect is so strong. Okay, it might happen. So we can't really rule this out. But in empirical, we're never able to see this one. Okay, so I mean that's why now it's still safe for us to assume your price would go down. Sorry, your demand will go down as price goes up, or your demand goes up as your price goes down. Okay, and that's why we see there's a price war, right? We see firms compete to lower the price rather than compete to raise the price. Okay, so more often, so I think it's more like some theory people or empirical people want to work on it, but it doesn't concern us. Okay, and the next is what we learn, what we call substitute and complement, right? If the other good, the price goes up and your demand goes down, okay, then they're complement, right? Because other good price goes up, then likely the other good, the demand goes down, right? And your demand also goes down, then that's why they call complement. Okay, the idea here is assuming ordinary good. Okay, assume all the good ordinary. Okay, because the good J, the price goes up, right? You assume the consumption of good J goes down, right? And because the complement, they tend to consume each other at the same time, so that's why it goes down. It's called complement and causative. Okay, so this is the later you see we will take away the gross, we have the net when you have compensated demand, but this is just assumption. Okay, so there's nothing but definition. Okay, so there's nothing to understand except you know it. That's they call it. So there's nothing to remember other than you know the name. Okay, but unfortunately there are many papers that just write basically, okay, they are gross complement, and that goes on assuming you know what they mean. So that's why we need to introduce the concept here. Okay, that's what it means. Nothing very deep. Okay, and the next is okay, somewhat I would think a little bit technical. Okay, usually you don't really need that, but we just need it. Okay, so here is called elasticity of substitution. Okay, so the easiest way to define the most compact one is like this one. Is the how the percentage change in the price ratio change percentage of the consumption, relative consumption. Okay, and usually when you write this, turn out to be like this complicated object. Okay, and because in optimal price ratio is same as the MRS. Okay, so just saying change the MRS, how it changed this one. Okay, so it looks very complicated. Okay, and usually this guy is a pain to derive usually. Okay, but unfortunately this is a very useful and very often observed utility form. Okay, although I know this looks crazy. Okay, I mean, who is going to derive it all the time, right? But the fact that turn out that this form, okay, adding some exponent together is a very convenient thing you can find out in the economic literature. Okay, either in macro or trade or IO, it's so common, it just use it. Okay, and this is a new thing invented in the 70 and 80 by Dixit and Stiglitz, and also Goodman. Those all important paper. They use this one, and this one have a not nice feature. Okay, because good thing is about empiric about this is this thing later you see by changing this sigma. The good thing is changing the sigma, you can have different format we have, right? Sigma, sorry, delta equal to 1, you have plus substitute. Delta equal to 0, Douglas, and delta equal to negative infinity, you have perfect complement. Okay, so this is rather convenient when you do empirics, right? Because this is a 3 basic extreme form, and by adjusting the sigma, sorry, delta, and you can do empirics conveniently, and mathematically they're rather convenient. Okay, and also this form has a good a lot of good property we don't describe here. Okay, but the thing is, like, you have one idea is that you have n different commodity, right? And the good thing about this is when you add more commodity, okay, this function usually stay the same form. Okay, you just change to n plus 1. Okay, then things usually would have no problem. Okay, that's different from talk about when you have perfect substitute, perfect complement. Okay, or Cobb-Douglas may be fine, but I mean, if you try to add one more good to the system, how you model utility is a little bit tricky. But for CS is rather simple. Just add one more term. Okay, so everything will stay the same. It shouldn't be an issue. And the other property we don't describe, but that's a reason why when you add one more good to the system, doesn't change that much. They explain why they use a lot of paper in trade or IO or macro, because often you have firm dynamics, one firm enter, one firm exit, consumer would spend on everything in that set, right? If the price is more, you spend less. So everything looks nice when you talk about the whole industry. Okay, as aggregate is a good thing. Okay, so that's the reason why this is a very common and convenient. Okay. And I remember in the last semester I give this as assignment and they all complain. Okay, so I mean we're not giving you for assignment for fun, but you should check. You could check out this thing. Is a very widely used one. Okay, the CES. Okay. Here I just got the definition here. I'm not going to go to detail. This is also very important when you look at the demand or consumer theory. There's also another elasticity. Okay. Note that before this is comparing price. Yes, substitution is comparing two different goods and two different price. Okay. Here is talking about within the same good I. Okay. Just change in the price, change in the consumption. Okay. That one is change in the price ratio to the rate of consumption. Okay? So that's a little bit different. Okay. And this one is often used also in macro. Later you when I talk about IO, competition, those will become very clear why we talk about this. Okay, because that is what we call the inverse elasticity rule. So or we say the markup, how the market price compared to the marginal cost is actually closely related to the elasticity of demand, which we will learn later. Okay, but we just define this at the moment. Is the how the price percentage change affecting your demand. Okay, so which means that 1% change in the price, how it affect is consumption. And you may ask for those who know and want to do empirical, this actually is very convenient expression, right? Because how can you find elasticity, right? You just regress the log of the price over log of the demand over log of the price, and that's it, right? Suppose you don't have any problem of the simultaneity, right? Suppose you can just run simple regression. I mean, of course, that'd be easy, but anyway, it's not that complicated. Okay. If you can able to solve your instrumental variable, you can solve this easily. But anyway, we're not econometrics class, but just this is a convenient thing. And turn out this is a free definition. Okay. Elastic demand, inelastic or unit elastic. It's very simple, whether it's less than -1 or more than -1. Okay. Just definition. Okay. So there's nothing but definition. So I guess I don't want to spend more time on that because all of them are just definition. Okay. Just remind you, this is nothing to derive, but just you know or you don't know. Okay. Just definition. So I don't want to spend time on this. Okay. Because there's nothing new here. Again, the definition is instead of talking its own price, but other price. Okay. So that we call the cross elasticity. Okay. And these are only important when you're talking about one-line regression. For those from real estate department, probably you run regression, you would do a lot of this. Okay. But I don't think for our purpose, I don't think we need to worry about all this stuff. Okay. And this is finally come to income elasticity. I just define it because just sometimes you need to know what are they, right? Okay. Now I guess it's good time to go to the next one. It's called the indirect utility. Okay. That is a side product of what we do the utility maximization problem. Okay. So remember the optimum bundle from this maximizing utility exercise, okay, is the Marshallian demand. Okay. But what is the utility? Okay. The utility obtained is called indirect utility function. Okay, it is based on the price and your y. Okay, based on income or your price, we get this indirect utility function. And you may ask why we care about this part. Okay, and this is very important for empirical, right? Because we can observe the price, observe your income, right? And this is more something you can easily measure compared to others, right? Suppose you are assuming that some form of utility, indirect utility function, right? Then you can easily do things, right? Compared to simple utility, right? Because you can always make an assumption on this form, right? And you can start one regression, right? And then you can avoid the problem of assuming anything about your Marshallian utility, right? Because if you assume Marshallian utility, right, then you have to go all through all the optimization to get what you want to do, right? And if you just assume this part, right, then things become easier. Okay, and indeed, you see some of the model that people just assume directly the indirect utility function. Okay. So without, I mean, it's very natural. You would expect, of course, you have to prove it, but the result of indirect utility function is just you get back the original utility, put the Marshallian demand in, that would be the answer. Okay, I don't think I need to explain this because but of course you look at textbook, they actually prove it. I mean, of course, you can believe it without any proof, right? Okay. So you may ask why we care about all this. Okay. At the very end, this is important. Okay. The main important thing comes from the last one, but we just go over one by one first. The fourth is the most important. The first one is the following. It's very simple, right? You will expect the same. If your income goes up, right? You cannot worse off, right? Okay, so that's why utility cannot go down. Okay, that's why you have this, the first one. Okay. The second one is also very trivial, right? The price goes up, you cannot be better off. So that's why this guy. And the third one comes directly from the homogeneous degree ratio of the your demand, right? Double your price and income, don't change your consumption. So the same, double the price and income, don't change your utility. Okay. So the three are very simple. Okay. So that is, as I said, it's comparatively easier than Marshallian demand because you know everything, right? Last thing is the most useful why we study this is the last one. Okay. Last one said the following, which if we have time we can prove. The proof is not difficult. What it said is the demand for good I will be negative of a ratio, which is the numerator is the indirect towards the price I, denominator towards the income. Okay. You may ask, hey, why I care about this? Okay. The reason is as I said, if you can estimate the V, you can estimate the demand, right? So once you have the V function, then the demand is very trivial, right? So that's why if you're able to estimate or figure out the way to have the V, then demand come immediate, right? So that is you don't need to go back to utility which cannot be observed, right? You can observe the P, observe the Y. If you're able to estimate the V, then you're done. Okay. So that's why they call Roy identity. So as I said, I don't think I need to prove 1, 2, and 3. Just go to the 4. The 4 actually is not, the proof is not complicated. Okay. because V is the optimal value, okay? We just by M.Phil theorem, okay? We differentiate respect to Pi is the lambda xi. You differentiate respect to V is y, okay? So that's why you divide, you get this guy, okay? So just directly come from M.Phil theorem, okay? So you may ask, just if you don't recall what M.Phil theorem is because V is the optimal value of this fund utility, right? M.Phil theorem basically said the following: you differentiate P, okay? You only need to worry about the direct effect. You don't need to worry about how P changed the demand structure, change this guy. No, you just need to only care about the final, to only cover direct effect, because indirectly change in P can change your consumption, right? And also change utility, but you don't need to worry about it. Actually, in the reality, they cancel out. So you only need to worry about the direct effect. Okay. I hope you learned M.Phil theorem before. It should not be an issue here. Is that okay? Yeah. Question? Okay. So very quickly, we derive our function. Okay, here. I mean, we will do something like this in the assignment. Okay. I'll give you later today. Okay. The assignment put on the blackboard. Okay. So if utility here, okay, your Marshallian demand is here. So indirectly is very simple. Just put it inside. You're done. Okay. And you can check the Roy identity by yourself. Right? You can differentiate this with respect to Y, with the price to give you back the Marshallian demand. Okay, you check it by yourself. Okay. So, and is that okay? So if you are okay, then we are going to consider another problem. Okay, we end with the utility maximization. Okay, for sure we have many slides that talk about definition. Okay, I mean you may or you may not remember, but that's not very important. When you need it, you can just go back and check. Okay, so what you remember from here is you know how to do Lagrangian. Okay, how to derive the Marshallian demand, how to understand how to derive the indirect function. Okay, and that's it. Okay, others are just for definition. I mean, I put there because I will be too lazy. Don't talk about this in the slide. I mean, already cut the things that, or already cut many things that is not important. I mean, if you try to check the textbook, there will be, way more than I put here. So already, I think I already keep the material minimal. Okay, but we don't still have enough time to cover everything. So I just put there. If you're interested, go ahead. But I think I already keep the minimal stuff. Okay, so don't blame me for 100-page slide. I think it's already very minimal already. I already cut everything down to the thing I can't cut. Okay, further. So the next is this is rather related, and of course, many times you will see, right? Is you want to maximize your utility based on budget constraint. Okay, and in this particular simple problem, okay, you can consider the other way around. Is minimize your expenditure to achieve a minimum utility. Okay, and you would ask why we have to care about this approach. Okay, and of course this is important in mathematics because they are the same thing on different perspective, and it is sometimes easier to solve the problem this way, I would say. Okay, and in empirics it's also the same. So this is sometimes easier to think the solution the other way around. Okay, so that's why we do it, and and the other reason is also for the firm. Also, you will see. Also, we have this duality, right? You have a profit maximization problem, also cost minimization problem. Okay, and for the firm, they are not that equivalent. Okay, for the firm, the cost minimization is a smaller problem than the problem of maximization. Okay? But for individual, they're exactly the same thing. Okay, so you have to be a little bit careful about the distinguish two part. Okay. Okay, so there's a little bit careful about this part. It's nothing, but just graphically, if you see this diagram, then you will know this is nothing deep here. Okay, let me draw a picture here, then you will see this is a very trivial. Okay, so I have hopefully you can see. I don't know if you can see x1 and x2. I don't know whether you can see. I try to draw here.
I can see.
Can you see?
Yes.
Okay, so x1, x2. So what we learn is we have a budget line here. Okay, there's a budget line. And in the utility maximization problem, the budget line is fixed, right? What we're doing to do is trying to find the red line with many difference curves, right? And we try to find a particular line that is the optimal bundle, right? So we just like here we keep drawing the red line until we found a good thing, right? Fix the budget line, try to move around the indifference curve and figure out which indifference curve would actually solve the problem. Okay, and we can flip our mind reverse, right? We can fix a particular red line. So what we're going to say is, instead of fixing the black, we fix the red one, fix a particular utility. Okay, we adjust our budget. Okay, we want the minimum budget to achieve that particular utility level. Okay, so that you can see this two sides of the same coin. Okay, do note that this is different from what later you will learn in the firm problem. These two are exactly the same thing. Okay, but the firm problem is a bit different. Okay, because for the firm you minimize your costs. Okay, but it's different from profit maximization, because profit maximization will have things to the market, right? So here is for you the same. Okay, for individual, the two things is the same thing. Okay, now this problem, okay, like flipping the two things, right? Because you have a linear objective function, right? But the constraint is non-linear. Okay, but first thing is we want something like Bravard's law. Okay, whether the answer is at the boundary point or the interior. Okay, the first thing is very simple. Okay, actually you can think this is reasonable. The price is positive. Okay, everything is costly means, okay, preference monotonic, the more the better. Okay, in that case the utility must be binding. Okay, what it means that the solution cannot be, this one must be binding. Okay, you are not going to spend more, okay, to make it strict, right? Because strict you can cut some.
I got a problem. That is, if we only care about utility properties of its ordinal properties, is this is the numerical value of the utility has meaning.
Okay, so the question is why we care about this when this ordinal. Same for maximization utility. Why we care about maximized utility ordinal? Because the order would matter. With maximized utility means that we choose the best bundle. So here is the same idea. We're telling us achieve a particular utility. Okay, then what kind of bundle to achieve that one? And you may ask, I monotone transform this, I also monotone transform this, there's no problem. So if I do monotone transformation on this thing, doesn't affect our conclusion, because this is going to solve it for every single U bar bundle. Okay, every single minimum utility level. I'm not sure I answered your question, but because when we solve this, we fix our utility. Okay, put it this way. When we solve this problem, okay, your utility function mean fixed. We're not changing our utility representation.
But I question, does the numerical value of the utility function has
Just order property, ordinal. So, but we are not doing any subtraction. So do you know that when ordinal means that the distance has no meaning, right? Higher, just higher. The difference of them has not particular meaning there. But we are not doing this operation. So we are not doing, just comparing. We are not, because ordinal means just compare. Okay? We just compare. As long as it's bigger, that's fine. We're not talking about minus this is bigger than certain number, then it can be easy. We just use the order. Okay? It's a good question. Yeah. So that's why we just use the ordinal property here. Okay. If you use the cardinal, then it's easy. Okay. You may issue here. Okay. So do note that this problem, okay, just a very good question is this utility function is taken as given. Okay. Of course, not changing this one. We're changing, just change the bundle here. Of course, as we said, price taker. So all the price remain the same. Okay. So that is an important thing. Okay. And just go back to here is positive price, monotonic preference. We must be binding because the idea is very simple. Okay. If this is strict at the optimal point, right, which means that you have higher utility than the minimum, right, then you can just buying less of something, right, and that will reduce utility, right, because price are positive, you reduce your budget, right. So that means the original proposed solution cannot be the solution. But let me repeat the statement. If at the optimum, this is not binding, okay, then it means that you can reduce any of the thing, okay, by epsilon, okay, and reduce your constant by epsilon, right? This inequality still holds, right? Because you assume some continuity in the preference, okay. Okay, so that's why it's there. So must be binding. So this is like the Wawa's law idea, right? Wawa's law is saying that the budget line is binding, right? Because of if it's not binding, you can spend more, and your preference monotone, you would go ahead. Same idea. Is that clear? Same as the Wawa's law. I would say. Okay. And here's the Lagrangian. Okay. Oh, I should use the green color for that. But so this is the problem, Lagrangian, and you derive. Okay, and you can see based on this first set, right? This is same as the MRS, same the price ratio. Okay. The last one is the utility, just the constraints binding. Okay. So that's why the same result, right? Because this is the same thing as the utility maximization problem. Okay, the same thing. There's nothing new here. Okay, and here, as the utility is like the strictly causic concave, actually you can prove this is unique. I didn't put the math here, but you know it must be unique, right? And that is called the Hicksian demand. Okay, do note that the Hicksian demand is almost the same, except that we give the utility U. Oh, typo. That should be U bar here, because the U bar here is U bar. So this should be bar here. sorry for the typo. Okay, because this U bar is a number, all right, and you put it. So just to iterate, this is a Hicksian demand is you give me the price, give me utility level, I can tell you what kind of the bundle I'm going to consume. Okay, and compared to the Marshallian demand, the Marshallian demand is give the income, give the price and income. I tell you how much I consume. Here is you tell me the price and my utility you want to achieve. This tell you what you consume. Okay, so this Hicksian demand is somewhat we may think as some of you said. I mean, my utility is ordinal, so it's kind of not very observable. Okay, you can't really observe it, right? It's very hard to observe. Okay, but later you will see this is more appealing than Marshallian demand. Okay, later you will see because people making decision based on utility, right? So this one actually has a better thing than the Marshallian thing. But anyway, let me quickly go into the result here. Okay, here is nothing new, but you can imagine this is very natural. But Hicksian demand, you double the price, okay, should not change anything. Okay, homogeneous degree in prices, right? Because of what, remember where you come from, this is coming from this statement here. Okay, look at this problem here. What matter is the price ratio, right? The price ratio should be equal to MRS, right? So if the price ratio, the relative price is not changing, you would choose the same combination, right? Say here what it happened is you double the price, okay, or make the same proportion of the price. I just spend more money, the same, double the same amount of money, I achieve the same utility, right? Okay, so that is nothing deep there. Okay, and now here at the end of the day, luckily with something like this, increase in price, okay, you always lower your Hicksian demand. Okay, so at the end of the day, luckily we have something what we want, right? Although it's not ideal. All right, at the end of the day, we have this. We have X and the P. We have a downward sloping demand. Okay, but this downward sloping demand has to consider the Hicksian way. Okay, and later you will see whenever Hicksian means we ignore the income effect. Okay, and that's what happened when we talk about IO or a lot of the model is when you consider the market is very small compared to the whole market. Okay, because suppose you consider the market of soft drink, which is small compared to the whole economy. Okay, compared to the whole people's consumption. In that case, income effect is very small. When income effect is small, later you will see it's actually the Hicksian demand. Okay, so what I was trying to say is the Marshallian demand, Hicksian demand are the same, will be very similar when there's no income effect, which we will define very soon. What is income effect here? Okay, when no income effect, the demand function is downward sloping. Okay, so that's why you look at a lot of IO model. You will often see they say, okay, the income effect is not there. We can safely assume downward sloping demand. Okay, in the earlier literature, but I think now no people emphasize in the paper. But that's the reason why they talk about this. Okay, so that's why at the end of the day, we're lucky we can still have a downward sloping demand. Okay, and we're pretty sure to say it when the income effect is not strong. Okay, of course, income effect is strong, then we have to be very careful. But up until 782 pages, we get something. Okay, unfortunately, I mean it's okay. I mean it's okay. We just make some assumption. We know when the market is small compared to the whole market, no income effect, we safely can assume this now at the end. Is that clear? I hope that I understand the goal of all this crazy thing. I mean, maybe even crazy, but all this complicated thing, at the end we get it. Okay. I'm not going into detail to prove it because I think it's it requires some math, which I think most of you will not care. Okay. Okay. The thing is how to prove this guy. The idea is to prove this is coming from later. The next function we learn is called the expenditure function, and we prove that's concave, and this one will be because concavity. And so what we're going to say is we have an expenditure function, and the first derivative will be the Hicksian demand, and we saw the expenditure function is a concave function, and that's how we prove this. But I guess we don't want to spend time on this proof. But you will see how we derive it. Okay, you will understand it when we talk about the expenditure function. Okay, so we just skip the proof for the moment. We know how to do the first one, but the second one we will just do it after we don't. We only need to prove it is we will show you the expenditure function is concave, and because we derive because the expenditure function, you take a derivative, it gives you the Hicksian demand. Okay, so that's why this is a direct consequence of that. But I don't see I need to consider it here at the moment. Okay. For the moment, let's give an example to see how you derive this expenditure function. Sorry, the Hicksian demand. Sorry, Hicksian demand. The same thing, right? The price and the Lagrangian. Okay. And then you derive xi, the p1 and p2, and then same for this guy. Okay. And you look at the first two equations, it gives the same thing, MRS. So same as the utility maximization problem. Okay. And then what you're going to do, right? Once you did that, right? You put x2 is equal to p1 over p2 times x1. Put it into here. You solve it out. Okay. You can get this one. Okay. Oh, sorry. You just put this to here. Sorry, just put this into here. You can solve this one. Okay. So nothing particular deep here, just like the Hicksian demand, it just depends on utility level and multiplied by the ratio of the prices. Okay. So there's nothing very deep here except this is the function. Okay. Now there's some terminology. I don't think I need to talk more than just telling you if you replace this Marshallian demand by the Hicksian demand, right? Then you have to, because of not gross, it's a net. Okay. And later you see you call net because we don't have income effect. That's why net of the income effect. That's why the previous one is a gross, but now we have net. Okay. But it'll be clear later what you mean by the income effect. Okay. So we have this, what we call the Slutsky's equation. Do I derive that? I derive that. Okay. I think we derive this, talk about this a little bit, and then we'll break. But I think we're almost done for the demand. Okay. So this Slutsky equation, okay, is the mathematical presentation of this diagram. Okay. If you learn the intermediate, that will be easy for you. Okay. So let's just start from the following. Start with the most left dot here. Okay. This original case. Okay. This original Marshallian demand. Okay. Now consider the price of good one goes down. Okay. So you change from this budget line to this one, right? So end up here. So this for good one, change from here to here is called the total effect. Okay, represented by this guy, the left-hand side. Okay, and later we will show you. Okay, you can do a hypothetical middle step. Okay, what we're doing is we draw parallel lines or the budget line, move down a bit or move up, depends on scenario. Okay, move up and down, and keep this utility constant. Okay, keep the original budget. Okay, you move it until you see a tangent. Okay, and from original bundle to this middle bundle, we call this substitution effect. Okay, because this is just change of your demand, keeping your utility constant. Okay, and what's this? This is just the Hicksian idea. Keep the same utility, change your price. So this is the Hicksian part, and this is the income part. Okay, because this the same, just this same price. Okay, just change the income. So that's why this income effect. Okay, let me repeat the statement what we're doing here because it's so important. I have to say it again because every time you will say the most crucial part from demand theory, right? Besides we derive this, is this. Okay, so this graph is the most important thing you want to remember from this class for this topic. Is this one. Okay, you have original bundle is here. Okay, this is a consumption, and then now the price change. Why you flip over this? Because price of good two is not changing. Okay, so this you can consume. If you spend all your money on good two, you can still. Don't know whether you can see. Can you see? Maybe just show here. If you try to steal on the good two, you can still consume it, right? So you can still consume it. Okay. Now from here up to here, why is called total effect? Actually, this is called the Marshallian, what the Marshallian demand is capturing, right? Because you just rotate, you just turn the price. Okay. This is from one Marshallian demand to the other Marshallian demand. Okay. So this is called the total effect, or what we call the Marshallian demand effect. Okay. And from this red bundle, where come from red one is you hold your utility the same. Okay. You just keep rotate the price ratio. Okay. Or you draw the parallel line. Okay. So that you keep your same utility, but under the new price, which bundle you're consuming. Okay. Repeat. The red one is you keep the original utility. Okay. And you change the price ratio to see which bundle you're consuming. Okay. The change of this is called substitution effect. Okay. But indeed, you can see this is the is a Hicksian demand. Exactly. Okay. Yeah.
When we got the same result, if we change the stakeholder, for example, we had first check the income effect and by expand our budget line and then we check the substitution effect when we got the same result.
So you mean I go the income effect first? Yes. So you are saying, okay. So so the question is being asked is if I go from I do not do the income effect, I do the income effect I move this on here. I figure out this utility. But that is called the Slutsky's substitution. So we have Hicksian substitution effect. You're talking about another thing. So actually, you can check the Mascot Winston Green textbook. They will tell you that for our purpose, it's no difference. So you can check the textbook. But this is the classical way people do it. So they're different. I mean, so in short, they're different. But for our purpose, it's not. There's no difference. Okay. So this is the Hicksian demand. Okay, and this is the income effect. Okay, the reason why we want to do this is because we want to compare the Marshallian demand, the Hicksian demand. So this is more direct. If you consider the compensation in this thing first, and then the other route will be different. Okay, and later you will see when I talk about at the end of the field slide. Actually, there's some issue related to what you said. When we talk about compensating variation and equivalent variation, that is actually in your mind. But for demand, for purpose, we just do this and
and that. Okay, do the Hicksian compensation, and then substitution, and then do the income effect. Okay, so let's prove quickly. I mean, prove this. The per price effect is actually consists of 2 parts. Okay, so the Marshallian effect is actually 2 parts. Okay, so that's why I always said. I mean, I just said, right? You can imagine if there's no income effect, right? The price goes up, always move along this indifference curve, right? So it must be the demand function must be downward sloping, right? Because it's like this, right? It's going down on this way, okay? As long as you have monotone preference, right? The indifference curve must be like in this way. But anyway, let's try to give you some idea why this proof will work, okay? So the proof is not difficult, so let's go to it together. Okay, not working, so let me do it. Okay, so the proof I do rely on, we know the expenditure. Let me talk about expenditure first, before otherwise I cannot give the proof. So let's say the proof, and then we try to go back after we done with the expenditure function. Okay, sorry, I should reverse the order. Okay, let's finish this thing first. Okay, the expenditure function, okay, is nothing but just the optimal value at the EMP, same as the indirect utility function. Okay, just telling you that it's the money you will spend. Okay, I give you the prices, and I give you the utility you want to achieve. Okay, so this is the expenditure function. Okay, and you can easily see that this is coming from just putting in the Hicksian demand there, multiply the price, give you the expenditure function. Okay, so there's some property here. Okay, first is if you double the prices, you double your expenditure. Okay, the reason is very simple, right? Because your optimal bundle will be the same because the price will be the same, not changing, right? So you double the prices, you just consume the same bundle. Okay, same bundle, just the total expenditure just double up, right? Just to repeat, the argument is because you are not changing your optimal bundle. Okay, you double the price, you're still doing the same bundle because the price ratio will be the same. So just double your expenditure. Okay, and probably you may ask why I care about XD1, because as I said, I mean, if you know the Euler's theorem, there are many properties you can derive. So that's why it's an important property. But for us, it's not big deal, except knowing this is sufficient. The second one is non-decreasing in prices, right? So if your price goes up, your expenditure cannot go down. So I think it's simple. Okay. This one, okay, deserves some discussion. Okay. It said I have a price vector 1 and 2 and a linear combination of it. Okay, what is said is the combination of expenditure, okay, is less than the average price. Okay, looks a little bit tricky. Do I prove it? Okay, I do prove it. Let's see, do I want to prove it? Okay. Maybe I can prove it. It's not something terribly difficult. So let's prove it because the argument is not complicated. And because we needed to talk about our Sharpest lemma and all the things, so I cannot Just skip, okay? So, but the proof is very simple, just one line, okay? So consider X1 is the bundle that achieved the minimum expenditure at P1, okay? X2 is achieved in P2, right? To get this utility, and XT is also the same, okay? So because X1 is the minimum expenditure, right? So you must be spend more time at the same price at this bundle, right? Because you achieve, you're doing the minimum expenditure, right? So the same for the second one, right? This less than this, okay? Now, it's rather simple. Now here you can see why this is true. This time this, and this time this, right? Because this guy is exactly this guy, right? This just x1, right? P1 x1 is P2 x2, right? And you can replace it by this less than xt. Is that clear? Is that clear? Okay. So then this, right, is just pt, right? And this same as ept. So that's why the linear combination of expenditure, okay, is less than expenditure of linear prices, okay? So that means that this is a concave, okay? Itself is not very important, okay? This is important because this, when we prove concave, together with the following, the surplus lemma, this is sufficient to prove this downward sloping demand, right? Because this is concave, okay? Then the second derivative would be negative, okay? Because you differentiate this again, right? Because it's concave, right? So differentiate again, this become negative, right? So that means that the Hicksian demand is negative. So that is the reason why. And you want to ask why this surplus lemma hold? Okay, it's also very simple, just directly following from the M.Phil theorem, right? Because you differentiate this respect to price, nothing is here, right? Just left any element there. That is the Hicksian demand. Okay, so that's M.Phil theorem. Okay, so let me have a break after a 1 minute talk about this. It's very short. Okay, so we have talked about this utility, right? And this is our Hicksian demand or compensating demand. Okay, and then what is expenditure? It's just P1 times the Hicksian demand plus P2 times the Hicksian demand. Okay, so that's it. Okay, and yes, so after the break, we will just go to the Sluxy equation and consider welfare, and then we can go to the firm. Okay, so let's have a break of 10 minutes.
So I guess we know the this concave in price, okay, and take the first derivative is this one, right? So we just go back to thing we missed before the break, right? We say this is negative, right? The reason why this is true is the fact that concavity, right, in price imply the second derivative is negative, right? And the Sharpless-Lammer said this is the first derivative is the Hicksian demand. So when you differentiate both sides of the price, right, this guy is the second derivative, which is negative. It's non-positive, right? So that's prove the that prove this negative slope Hicksian demand. Okay, so that is what is supposed to be. Okay. So lastly, I want to spend some time on this. Okay, there's some proof, but I just want to show you this is the very simple proof, but which is not is in the black form, so it's the technical thing. Okay, and I'm pretty sure that you will never need them again, but just let you know the idea. So what we base on is saying because the EMP and the UMP are giving the same result, right? So that's why the Hicksian demand, okay, at a certain level of utility should be same as the Marshallian demand if your income change based on the expenditure function. Okay, so that is you can easily see why this is true, right? Because the income is actually changing anyway, right? In this setup. Okay. So what I'm going to do is you differentiate this equation with respect to price. Okay. And the Hicksian demand only have price, right? But the Marshallian demand, you have two elements with price. Okay. Because for Marshallian demand, you change the price, you change two things. First, you change your first argument, give you this guy. The second, you change your income as well, right? So you differentiate this and this by the chain rule. Okay, first argument here, second argument here. Okay. Now it's very simple. You just flip this to the other side. Okay. Then will be the price effect is equal to the Hicksian thing, income effect. Okay. And the free part already, right? So try to see we can rewrite this part nicely. Okay. But it's almost there. Okay. Because you differentiate the expenditure function towards the price is Hicksian demand. So this guy. Okay. So that's why you can rewrite in this way. Right? Hicksian demand is same as the Marshallian demand, keeping the utility same. Okay. So write this way. And E
right? Expenditure is just income. Okay, so that's why you have this equation. Okay, so we just it's one step by step. Okay, so of course and final step involved is how to change this Hicksian demand, because at the optimal compensated demand, right, this utility can be replaced by the indirect function. Okay, and in that case you can replace it by y, so that's why you can do things without Hicksian demand. So just at the end replace this guy. Okay, so of course you would think all this very technical, okay, but Slucky equation, it just basically talking about this graph. When I talk about the prices is very small. Okay, this is a big price changes a little bit, right? But you can see the free thing. But just saying that it just you can decompose in the free part. Okay, and the good thing, the important thing about this thing is trying to tell you that, okay, if this part is very minimal, okay, so you can basically assume Hicksian demand and the Marshallian demand are very similar. Okay, because this is something we will need when we talk about the following or the final thing. Okay, just one more thing about this particular slide. Okay, it's about the how do you compare the Hicksian demand and the Marshallian demand. Okay, as I said, if there's no income effect, okay, then the two curve the same. Okay, now if it's normal good, okay, suppose we start from this point. Okay, this is the Marshallian demand. Okay, and you may ask why, if normal good, why the Hicksian demand is like this? Okay, it's very simple idea. The price goes down, you consume more, right? If normal good, the income effect is positive. Okay, so when you look at compare the Hicksian demand and Marshallian demand, the difference should be the income effect, right? So because it goes down, the income effect positive, so you would have this one like this. Okay, and reverse, you have this because the income effect is negative, right? So it should be go down further. Is that clear why this is the case? Let me repeat the statement. The difference between them is the income effect, right? Let's repeat the difference between them is the income effect, right? Because normal good, the income effect when the price goes down is positive, right? Because the price goes down. Okay, what's the income effect? The price goes down, right? Even you consume the same quantity, right? You have some money left. Okay, how do you distribute this money left there? Okay, somewhat like this. So this is positive, this is negative. So go this way, go that way. And inferior good is other way around. Okay, so because the income effect is negative, so that's why you go this way. Okay, so this is how this graph looks like. Not very important, but it will be important when we talk about the following: welfare. So looking at the welfare is very important thing when you talk about policy or talk about see whether consumer are happy, and when you talk about designing a system for computer scientists, right, you want to make sure that they are happy. So that's the measurement of welfare. Okay, so we focus on the simplest case, which is we consider consumer have initial price 0 and income is y. The income is kept the same. Okay, so the change is I have priced into P1. Okay, now look, suppose you have indirect utility function, right? So previously the consumer is like this. Now the consumer is like this. Okay, so we want to know how consumer better off and worse off, right? And how to quantify this change. Okay, and
Of course, here I talk about change in price, but in the practice, when you do modeling, you may say, suppose the firm is using a new advertising channel, change the supply chain, or the market structure change, right? Compensation regulations allow one more firm into the market, okay, so on and so forth, right? So that is the same method you're doing, right? And in economics, people all the time talk about consumer welfare, okay? Less so when you look at the marketing literature, they care less about this. They care about more the firm side, how the firm make the pricing decision, okay? But when you talk about operation research, talk about the user experience, then we talk about this, okay? So what we are trying to do in the set of slides is trying to justify the following thing, okay? Here is we have good demand, okay? We have the downsloping demand function, okay? And usually we call this Q, right? Just single good here, single good well, okay? So the question is, usually you learn from your intermediate course is, suppose this is the price, P0, right? And now the price goes down to P1, okay? Of course, the consumer is rather happy. The question is, can you quantify how much happier they are, right? And you learn that from your intermediate or basic micro, they will say this guy, okay, is the change in consumer surplus. Okay, this is what you learn, but they never give you the idea why this is the case, right? Because demand is not something related to human preference, right? So what's the foundation for that? So we're trying to show you that this consumer surplus is an approximation or a middle ground of what we're supposed to measure. If you put this into our utility, put it in the preference perspective. Okay, let me repeat the statement here. What we're doing for the rest of the slide is trying to show you that you learn in your intermediate micro, you try to evaluate this change in consumer surplus as a measure of how consumer benefit, okay? And we can put it into the preference idea, okay? Use the preference framework to say, okay, in fact, this is a good measure, okay? It's not the exact measure, but this is a good measure, okay? I hope this is clear now. So quickly we go to explain what it is, okay? Because this doesn't mean a lot of things, okay? We want to look at the preference, look at the utility. Change in demand means very a thing, okay? So let's see the following, okay? Let's try to measure the changes in terms of money, okay? In terms of money. There are two ways to measure the money, okay? First is look at, question is, suppose now before the changes, this is how happy he is, right? At this income, this is the old price, okay? This is how happy he is at the beginning, okay? Now he got a new price, okay? How much income I can take away from him to make him as happy as before, okay? Go back to here. The question is, if I cut the price, okay? How much money I can take away from him so that he is as happy as before, okay? It's a money measurement. Okay, is that clear? What is going on is original happiness, okay? New price, how much money I can take away from him. Okay, that's called a series. Okay, very soon we'll justify why this is the case, okay? But this definition. The next definition is the following, okay? This is the pay utility, okay, after the price change. I'm asking in the original case, how much money, okay, I can give him to make him indifferent. Okay, suppose you are in the world after changes. Okay, how much money I can take away from, how much money I can give you in the original case, so that you don't do the change. Okay, is that okay? So suppose here I lower the price, right? Then I need to give you money, right? So that you would be indifferent, right? I don't implement the change. Okay, then how much money I give you? So how much? Is that okay? Okay, these two still a little bit not very intuitive. Okay, let's see how it can be derived. Okay, this turned out to be equivalent to the following. The CV and EV, okay, just go back to this, is CV is how much we need to take away in the new scenario. Okay, turn out this is equivalent to the following. CV is different between two expanded function. Okay, in the new price, this is the amount, this is new utility, okay, minus the new price at the old utility. Okay, and if you change the price from new to old, it becomes EV. Okay, now repeat it, it's a little bit very confusing. Okay, CV is saying that, okay, this is the utility in the old day, the new day. Okay, look at the price. Okay, and I want to say, this is the compensation, or this is the changes it requires, right? Because now I'm here, right? And suppose the new price, I want to obtain my old utility. Okay, how much I need to compensate you, okay, to achieve the new thing. Okay, so in the old world, this is V0, right? You have the V0, right? Now the change has been imposed. It's P1 now. Okay, there's no way to go back to P0. P1 is new world. Okay, the question is how much I need to pay you so that you get back to what originally you're supposed to get. Okay, now the same thing, but now we want to say remain at the old world. Okay, and look at the utility. Okay, change in old and new, right? So this is difference. Okay, so you may probably still not really see what are they. Okay, I recommend you see this following diagram. I think that will be easiest to see. Okay, looks complicated. Okay, but let's see the following. Okay, so let's see the red thing first. Okay, forget the blue, only the red. Okay, this original bundle, this is a new bundle. Now I assume the price is reducing. Okay, and the red one is Hicksian demand. You know it, right? Hicksian, this is the consumption. Okay, and assume the price of good 1 is 1, good 2 is 1, P2 is 1. Okay, now so this is the old utility here. Okay, old utility here. Okay, and this point, okay, will be, okay, at the price 1, you consume the old using the old utility, right? Because why? Because P1 is P2 is 1, so that's why this is the expenditure at this point. Okay, so this difference is what we call the CV. Okay, is why is the case? Right, this is CV because CV is defined as
Oh, I think that's a oh. I'm missing one thing. I should also write one thing also here. Y is P0 V0 but Y is also okay. So that's why difference is the EV. Okay, what you're going to do is this is exactly the income effect, right? It's the CV. So you just look at this. I look at the new price, okay, and this consumption bundle you see, and you try to see how much I need to compensate you, okay. So that's why this is the CV. Okay. The other way around is look at the following. The EV is looking at after changes is here. Okay. I keep myself on the new utility function. Okay. And the money difference between this and the original is the EV. Right? Because this is the changes from here up to here. Okay. So that is the big difference between the two. Okay. The proof, I think I can skip, but the idea is whether you want to looking at the utility of the old days, okay, try to keep this utility and see the changes, or you go back to here and see the changes. Okay. CV by the definition, right, is asking for compensating, right? So we just do the changes, how to compensate the difference, right? And this is the equivalent changes. It's just like I give you this much, you're okay to remain the same price as before. Okay. So what we are doing here is trying to quantify the difference. Okay. So that's definition. And okay, is that okay? Okay. So the difference main thing is the compensating variation is looking at original utility. The other one's looking at the new utility. Okay. So is the because of the surface llama, right? So the expenditure function is the integration on the Hicksian demand. Okay. So it means that this diagram is right if we are talking about Hicksian demand, because the area under the curve, okay, is actually measuring expenditure, right? And it's measuring how much money I need to get or to pay to accept the change or avoid the changes, right? So it means that if there's no income effect, right, these two are the same and will be same as the change in CS. Okay, this is the first statement. The second statement, which I don't think I have time to prove today, you can check out the graph, will be the following. If the good is normal, okay, or inferior, depends on what they are, EV bigger than EV and CS will be within the two. If inferior, also the same, but the sign flip. I think I drawn the new graph here, but I don't have time to go over. Okay, but what I want to emphasize here is the measurement of the CS in the literature is a good one. Okay, so that's why we have been doing all this consumer surplus calculation.
Okay, it's fine as long as the market you're talking about is small and there's no income effect. Okay, so just to justify why we have been doing all the consumer surplus, right? How is it related to a preference? So that is the added value of talking about preference, right? Because without preference, there's no meaning about talking about consumer surplus, right? What is consumer surplus measuring? Just to go back again, is measuring what we call how much, okay, we need to pay that guy to accept the price. That's why we call compensate, because the change has happened, we need to compensate, right? And that's what happened in the graph, right? Because now the change had happened, how much we need to compensate that guy, right? Or suppose the change happened, what is the property that is equivalent to what is not? Okay, so that is what it means. Okay, and when the income effect is small, it's okay to use consumer surplus. Okay, and consumer surplus is if you don't know whether the good is inferior or the good is normal, in that case, consumer surplus is always in between, right? So it shouldn't be. It's a good approximation to that. And of course, why we do this in our paper, because consumer surplus is easy to do, right? That's why I do it. I mean, one of the reason why don't we? The question is, why don't we just calculate CS, CV, or EV directly? Because CS is much easier to do, right? So, and now with foundation, and you should understand why not. Especially the income effect is small, which usually the case. When I talk about an industry, it's fine, right? When I talk about the whole set of economy, okay, when I talk about macro, looking at the consumer surplus can be misleading because income effect can be substantial. But I think it's okay. Okay. So let me briefly review what we have done today, and we go to talk about the firm thing. So we spent almost 2 classes to go over the consumer part. We skip a lot of proof because we can't really have time. But what we learn is we start from, beginning, right? We go back to the objective we learned here. Is we start from preference, okay, and go to utility, and we try to say, although we use utility, we understand what the preference in the back. Okay, and we learn my utility maximization problem. Okay, we know how to derive this too, and you will do it in exercise assignment. Okay, to do it. Okay, and your assignment will have 2 parts. One part is required you should do it. One part is challenging. So because for those, you don't need to submit the challenging part to me. Okay, you just submit the part that is required to do, which is supposed to be very basic. And you learn how to derive this, and this all will be in the assignment. Okay, and you also learn the consumer surplus. Okay, which justified by the idea of CV and EV. Okay, actually based on Hicksian demand. Okay, expenditure function. That's why we learn all this, although looks trivial. Okay, looks some technical and have application on consumer surplus. And we actually we care a lot of time. Okay, and I guess that's the end of our consumer part. Is there any question? I know we are a little bit rushed, but because we already over time a lot, so I cannot talk more on that. I hope this is okay. And for some of you will notice I uploaded lectures looks, which actually I prepared last year, but actually I didn't distribute last time because some of you emailed me last night about more advanced stuff. So here, I mean, in the notes, I have some more details and some more proof, which I didn't put in the slide, which actually because I prepared this handout first before I prepared the slide, and you can check it out. But I think it's almost the same thing. I just cut something out. Okay, but in case you want to know, you know what I missed and what are the reference, what are the math here, you may want to know. You can check it out. Okay, but it's not updated. But if you see any problem with the thing, let me know. Okay. So before, is that okay? Okay. Consumer, but remaining, I mean, less than 8 minutes. I want to give you overview of the firm theory. Okay. And want to discuss what we don't discuss in this firm theory. Okay. In this one, actually, it's much easier than the previous one. Okay. Because one of the easiest thing in this firm here we are working on is firm is just maximizing profit, right? Facing the constraint of technology constraint, how to combine input to make output, right? And when you look at the input market, it's also competitive, right? So it's a competitive input market. So how many raw material he's going to buy, how many labor he's going to hire, it's not going to change anything. Okay. So his price taker in the inputs market, and so that's why things become also easy, because it's also in the output market. He also price taking. Okay, how much he's going to produce is not going to change the market price. Okay, so there's nothing behavioral in this context, right? Because everything he faced is environment. He wants to maximize profit. Okay, and the profit is just price times output minus the price times the input. All the price are given, right? And what can transform input to output is given by his technological constraint. Okay, usually we make the assumption that we can solve the model, right? So that is not a big deal. Okay, so what we try to learn is, okay, just to apply what we do the consumer thing in this context, and this much easier context. Okay, so this one I will be even faster, go faster, because there's nothing deep inside. Okay, but that being said, I want to focus on this slide. Okay, is we assume the firm basically a machinery that is going to maximize profit. Okay, we basically ignore so many things, right? Because we ignore how the firm is being organized, right? We don't talk about the boss, don't talk about manager. Okay, don't talk about whether the worker would work, right? Whether organization economics, everything is gone, right? And we ignore the management issue. Okay, they are all very important, no doubt, right? And when in game theory or principal agent problem concept theory, you go back to those issues. Okay, say corporate finance, right? By and large, a lot of them talking about contracts, right? Because corporate finance is about a debt contract, an equity contract, all the things that can be explained by game theory, right? And how you in the human resources management, right? How you design a compensation package, right? Is also a game theory problem, right? And also you decide the scope of the firm, whether you want to vertical integration, how long the supply chain is doing, right? It's also an IO game theory problem. Okay, we basically ignore everything there, assume the firm is very small, and everything can be solved easily. Okay, it doesn't mean that this is the way we should do, but this is a good when we talk about the whole market, right? When you talk about specific strategic decision, this is not the only story. Okay, because where the firm is making decision that will change the market, okay, then things become different, right? Very often we will see one famous thing about Apple is like he is not going to minimize his cost, at least not the short-term cost, right? They are trying to say make sure that every supply would at least have more than one supplier. Obviously, it's not minimizing the short-term cost, right? Because you put everything into one, the cheapest guy, right? And of course, the price is cheap, the cost will be cheapest. But he's talking about the dynamic cost behavior, right? Because sometime in the future, that company may not be the lowest cost, right? And also the other thing is the bargaining issue, right? You don't want the whole problem, right? If I always only rely on one supplier, what happens if one supplier is not working, right? Or the supplier has too much bargaining power. So always try to have more than one supplier. Okay. So all this issue is all gone, right? But of course, when you learn game theory in the second half of the course, then you will know everything can be explained, or there's three to explain, right? So that is something we're missing. And another thing we have missed is about the scope of the firm, right? Here we don't talk about that, but that is a very famous thing. Is in economics, we always talk about market, right? There's a price that can exchange, right? Then why we need to have firm, right? According to the market is good, firms should be very small, right? We should have market for everything, every single thing, right? And what the Ronald Coase actually said is firm is exactly opposite the market, right? Because market allocate resources based on price. Okay, if the price go up and go down to optimally adjust. Firm is, or corporation is exactly opposite of that. Within the firm, is the manager decide how things being used. There are no internal price to organize it. Okay. The repeat is what I think is what Ronald Coase says. Firm is actually suppression of the market. Exit the firm is the market power goes away, right? Because it's not the case the price determine how we do things. Okay, that's the market, right? You don't have the market, right? Market say you want to buy bread, right? The bread has a price, right? You're going to buy you have a noodle, there's a price for that. That's how market allocate resources, right? But within the firm, it's not the price would say allocate which job get done, right? It is the case for say for DD driving, is like the price allocate, you decide where to get it, right? But within the same firm, right? It's not say the boss decide, okay, for the job of HR, $5,000, for the job of sweeping the floor, $1,000, cleaning the toilet, who's going to take the toilet for $500, right? Who is going to teach the micro classes, give you this price? No, right? Within the organization, is how to allocate jobs. It's not by price, right? The job that I get fixed salary, okay, and then he tell me what to do, I do. It's not the guy who put the price, I go to bid, right? Not the case. Okay, so basically, there's a lot of literature study the boundary the firm, limit the firm, when the firm should stop, right? That actually the M&A or those kind of thing, right? Whether we should outsource this, you should internalize this, right? All this theory of the firm, and people talk about contract and a lot of stuff, but we ignore. I mean, they're very important, and indeed, that is why B school is here, right? If everything can be solved by the market, right, then no use of the B school, right? B school is like managing how firm behavior, right? So, and if firm is just profit, simply price taking, profit maximizer, okay, then things are done, okay? But when we talk about this, the classical thing we are doing is how consumer behave and how firm behave, and we end up with equilibrium, determine the demand, supply, and the price, right? At the end of the day, right? What we learn in this framework is to derive the following, okay? And I will end on this. We want supply, okay? This is what we want to get, okay? And we want to get supply function when we end with this, okay? Do note that this supply function only exists when we talk about a perfect competitive market, okay? And later you will see when we talk about monopoly, oligopoly, Carnot, we don't have this. Okay. You will see why we don't have that, but because price and quantity is simultaneously determined in the system. Okay. But when the price taking behavior, we have this, right? Because why we care about this? Because you want to incorporate this, right? And we get equilibrium. Okay. So here we just try to give you the foundation to get this demand supply framework. Okay. And because this can explain a lot of things, so this is useful. But nonetheless, especially the supply, okay, a lot of issue there, because in the real world, the market is not perfect. Okay. And for demand, it's okay. We spend a lot of time because demand doesn't change much when the market structure change. People still maximize according to what we have seen. Okay. So see you next week. I don't have anything to say. I would put the assignment today or tomorrow. I think you have I know you guys are busy. Let's have 2 weeks to do it. If you think it's too easy, then I can make it 10 days or less. But the first assignment gives you 2 weeks to do it. They can tell me whether it's too much or too little. I make it easier this time, so much easier this time. So there will be some optional part you can do it, you don't do it, but the required part will be very simple. Okay, so that'll be an issue. Okay, I'll see you next week.